Okay, this is the first lesson for Unit 8. The notes that I'm using are in the Unit 8 notes folder, and it's labeled Unit 8 Thermochem, I believe. So Unit 8 is going to involve how energy plays a role in chemical reactions. So we're going to start out with these energy diagrams just to kind of get an overview of like what we're going to be studying. So in an energy diagram, the y-axis will have energy, and then the x-axis will either say time or progress or process of the reaction. And we've got a new variable that we're introducing, which is delta H, and so you might also see delta H on the y-axis as well. And delta H, as we'll talk about a little bit later, is we're just going to think of it as heat. Heat absorbed, heat released during a chemical reaction, and it represents a property called enthalpy. Okay, so this is showing the energy of the reactants, and that is the energy that is tied up within the bonds of our reactant molecules. And then likewise, down here, this represents the energy of the products. So we can see in an exothermic reaction that the change in energy between the reactants and the products are at a lower energy, and that's because heat is released in an exothermic reaction, and so that heat energy had to come from somewhere. So it came from within the reactant molecules, and then so that heat is released, and then the energy remaining in the product molecules is what we're showing here at this line. Now, we have all of these energy diagrams have kind of a little bit of a hill in them. And what that represents is something we call activation energy. Okay, and we use like an E sub A for that. And activation energy is kind of the energy that's required to get a reaction started. So we know, for example, that the materials that are on the head of a match, that they will react with oxygen and combust. However, they don't do that just by holding them up in the air. So we do have collisions, we do have oxygen molecules interacting with the head of a match, but we don't have it spontaneously bursting into flames. And that's because it needs a little bit of energy to get that reaction started. And then because it's an exothermic reaction, the combustion, then it then uses some heat from that reaction to start subsequent reactions and to kind of keep the combustion process going. So the activation energy is always going to be the energy from the reactants up to the top of this little hill here. And this hill is what we call, or what we refer to at the peak of that hill, is the activated complex, or later on when we get into kinetics, we'll think of this as what we call intermediates. In other words, the intermediates, these are things that are formed during the process of a reaction, but then they're also consumed during the process of the reaction. So they're substances that are not reactants and they're not the products. They're just an intermediate thing that is formed as the reaction progresses. Then our delta H, or the difference here, that's always going to be products minus reactants. So remember, when we use the symbol delta, that's always final minus initial. So if we're looking at something related to a reaction, we're looking at products minus reactants. And so we're going to make a little change because there is an error on the endothermic one. Here, for endothermic, we want to note that, again, the activation energy is always the difference between where the reactants start and the top of the hill to the activated complex. So that arrow should be long. It should be extended down to the reactants. All right, so let's look at some questions that you might see with these. All right, so first off, does it represent an endothermic or exothermic reaction? Well, here we look at the fact that the products are at a higher energy than the reactants, so this is going to be an endothermic reaction. And the delta H for the reaction, products minus reactants. So our products are at 100, and then our reactants are at 50. So that's going to be 50. And then the activation energy, go from the top of the hill is at 250, and then minus the reactants, energy is 50. So my activation energy is 200. And the energy of the activated complex, that's up here at the peak, so that's 250. And then the reverse activation energy. Now you'll notice in the quest, and typically when we're talking about the reverse reaction, that means that we've kind of flipped it. So we're starting with the products and then we are making the reactant. So we're going in the reverse direction. And you'll see that is referred to with a prime symbol. So anytime you see that little prime symbol on activation energy or on delta energy or delta H, if it's a prime, it's talking about the reverse reaction. So if we look there, if we're going in the reverse, then my products would be essentially my reactants. So the top of the hill is still 250, but now I'm starting at a value of 100. So the reverse reaction is going to be 150 for its activation energy. All right, so here, again, is this exo or endo? So here my products are at a lower energy, so this is an exothermic. And our delta H is products minus reactants, so 20 minus 40. And so that's going to be a negative 20. And in this negative, when we're talking about delta H or delta E, change in energy, the negative just means the heat is being released. The energy is leaving the system, going to our surroundings. So activation energy for this one, so it's at 100 and then minus 40. So that's at 60. And then the activated complex is at 100 for this one. And then the reverse activation energy, so still 100 and then minus, and this time it's minus 20. So the reverse reaction, the activation energy is 80. Okay, so now, all right, so at the beginning of these notes here, we have just some different definitions of energy, since that's what we're focusing on. And we will see that heat or thermal energy is what we are focusing on in this unit. Two terms that we want to look at is our system and our surroundings. So the system is what we are focusing on. It could be the beaker that contains the reactants. And then the surrounding is everything else. Because we're looking at energy moving into or out of our system, we always have to think about, well, what are we defining as the boundaries of our system? So in looking at the change in energy of a chemical reaction, again, that's going to be final minus initial or products minus reactants. And so this is, again, just another way of demonstrating that this is our exothermic process here, and then this one here where the energy is coming into our system, that's our endothermic. Now, one of the things we haven't really talked about before is when we are writing a chemical equation, how do we demonstrate if this is endothermic or exothermic? And the way we do that is for exothermic reactions, the energy, and it may say energy, or it may have an actual numerical value of joules or kilojoules. It's going to show up on the product side if it's exothermic. Okay, and then if it's endothermic, it's going to show up on the reactant side because we require energy to have this reaction occur. Now, when we're talking about chemical reactions, we can change energy in two different ways. One is heat, and the other is work. And what we'll see with work is that the way a chemical system does work is by producing a gas. Because the definition of work is where we have a force that is applied over a distance. And in a chemical system, the way that it does that is that we have a pressure that's being applied that results in a change in volume. So think of kind of like a cylinder and a piston, like what you would have in a car engine. And so I can do work, my system inside the cylinder can do work by a combustion reaction that creates gases that push up against the piston in the cylinder. And then if I'm going to do work on the system, I can compress the gases by applying an external force, or be a force from our surroundings onto the piston, which is compressing the gas that's in the cylinder. So we use the symbol Q for heat and W for work. And again, we're still using those same sign conventions. Energy going into our system is positive, so endothermic is positive, or the other one would be with work. You're looking for phrases like work that's done on the system. Okay, that's going to have a positive value, whereas for negative, with heat, it's an exothermic reaction, would be a negative delta E or negative Q. And then here we're looking for the work done by the system. Okay, would be the phrasing we would need to know that our W is going to be negative. So let's take a look. All right, so here we've got just some examples here. So here is in the first thing here, again, we are either adding heat to the system or removing heat from the system. And in this case, we have no work being done at all. However, here, if I have a reaction and it's in this container that has a cylinder with a piston on it, and so as our reaction occurs and it's generating hydrogen gas, we get a pressure that then forces that piston outward. So this would be an example of work that would be negative because it's work done by the system. It's pushing against the surroundings. All right, so law of conservation of energy, I'm sure you've heard of that before, meaning that the energy, we can't create or destroy energy, it just changes forms. And that is also referred to as the first law of thermodynamics. Basically, to state it kind of in an equation, the first law of thermodynamics says the change in energy of the universe is zero, meaning if the change in the energy of the universe is our system change plus our surroundings, well, everything that happens in the system, so if I have energy leaving the system, well, that energy is going into the surroundings. So our delta E for the system is going to be equal but opposite in sign to the delta E for the surroundings. So that's why when we add those two things together, we always get a net change of zero. That's conservation of energy. So now let's look at, these are a couple of units before we start looking at some practice problems. So joules, we've been using joules as our unit of energy. We can also use calories. That's another unit of energy. And here's our conversion. 1 calorie is 4.18 joules. Now, just to kind of clarify, that is a little c calorie. You'll notice whenever we do look at food nutrition labels, those are capital C calories, all right? And those are equal to a kilocalorie. So 1,000 little c calories is a big C calorie, which is like a food calorie, and we're talking about those. Okay, so let's read this question here and see kind of what these problems are going to look like. So here it says, if the expanding gases do 451 joules of work on the pistons. So that phrase right there implies that the system is doing work. So from that, we would say my work is going to be equal to negative 451 joules. And then it says the system loses 325 joules to the surroundings. So that means that my heat is going to be negative 325. So my delta E is Q plus W, which is going to equal a minus 325 plus a negative 451. And that's going to give us a negative 776 joules. And then it wanted us to convert that into kilojoules and into kilocalories. So kilojoules, we have 1,000 joules in 1 kilojoule. So that's going to be negative 0.776 kilojoules. And then if we want to go, so minus 776 joules. So to go to calories, 4.18 joules is 1 calorie. And okay, then 1,000 calories is 1 kilocalorie. So that's going to give me 776 divided by 4.18, and then divide by 1,000. So 0.186 kilocalories on that. Okay, so now in the next one, here they're giving me the work done, but they're giving it to me in terms of a pressure and a change in volume. So we're going to jump a little bit to the down in your notes to where you get to this thing right here, because this is talking about how we calculate work if we're not given it already in joules. So we're going to use this equation that work is the negative pressure times the change in volume. And again, change in volume is final minus initial. Now, this is our pressure there is in liters, and is in atmospheres, ATMs, and my change in volume then is going to be in liters. So that's going to give me a unit of liter atmospheres. And if we're going to add that to heat, which is in joules, then we need to have a conversion between liter atmospheres and joules. And so that conversion that we're going to use is that 1 liter atmosphere is going to be equal to 101.3 joules. All right. So now this equation and that conversion is not on the AP formula sheet. So this is going to be one that you'll need to remember, and hopefully we'll get enough practice that it won't be difficult to do. All right, so back to our sample problem here. So here it says we are compressing from a volume of 8.3, so that's my initial volume, to 2.8, that's my final volume. And then there's my pressure. And here it says we have a heat gain by the system. So that means my Q is going to be a positive 350 joules. So let's look at what my work is going to be. My work is going to be negative 1.9 times V final, which is 2.8, minus V initial, which is 8.3. So that's going to give me, let's see what we get, 2.8 minus 8.3 times 1.9. So I'm getting 10.45, and that is in liter atmospheres. And then now I have to convert, and 1 liter atmosphere is 101.3 joules. So times 101.3, and so 1,059 joules. And that's positive. So my delta E then, again, it's Q plus W, so is 350 plus 1,059, and So 1,409 joules. Okay, let's look at this one. So here again, I'm giving my work in terms of a pressure, which is 1 atmosphere, and then my V final, 29.1 minus 11.2. So here my work is going to be 29.1 minus 11.2. So I'm getting negative 17.9 liter atmospheres and 1 liter atmosphere, 101.3 joules. So times 101.3. So 1,813 joules. That's a negative. Don't forget that negative sign. And it says the heat is absorbed. So my Q is a positive 1,037. So my delta E is Q plus W, and that's going to be 1,037 plus a negative 1,813, 1,037 minus 1,813. So negative 776 joules. Okay, now we're going to talk a little bit more about enthalpy, or delta H. And one of the things that we are going to be looking at when we solve problems with delta H is the fact that it is what we call a state function. And a state function just means it's something that its value is not path dependent. Delta H only depends on the energy that it ends up at, so the energy of the products, and the energy that it started with, or the energy of the reactants. It doesn't matter if I complete the reaction. And remember, up to now, we've been using like a single balanced equation to represent a reaction. But you want to understand that that is just a summary. That one equation is just telling me this is what I start with and this is what I end up with. But there may be several different ways that we can make that journey from those reactants to those products. We might do it in 3 steps, or we might do it in 5 steps. Okay, so the key thing though is that it doesn't matter, the delta H value, it does not change depending on whether we do that reaction in 3 steps or 5 steps. It's only dependent upon the ending energy of the products and then the beginning energy of the reactants. So just as an example here, so say I burn like a mole of octane. Well, a mole of octane has a specific amount of energy in it. So that's the energy of our reactants. Now I can combust that octane just in an open container and just burn it. So there I have all of the change in energy is occurring as heat. Whereas if I do it a different way, so say I combust that same amount of octane, but I do it in the engine of a car. Well, now some of that energy is being converted into work because the gases that are produced in the combustion are in this confined cylinders in the engine. And so they are pushing up against the pistons, which is giving you the energy for the car to move. So in that case, some of the energy being lost is due to work and some of it is due to heat. However, the change in energy, the enthalpy of that reaction, is all based on the change in energy between our octane that it had at the beginning and the products of the combustion, which are the carbon dioxide in the water. So it doesn't matter. Work is not a state function. The amount of work done does depend upon the path that we take. But our change in energy or our change in enthalpy is only dependent upon the ending state and the beginning state. Okay, so we're going to jump down here. And the key thing is I put this in here because you'll see in your textbook that they have kind of this discussion about really what enthalpy is. And enthalpy is a combination of our change in energy and the work that is done. the key thing to remember is that most of the time we are doing reactions in open containers, and so the amount of work, if we are producing gases, so the amount of work that those gases are doing in kind of when they're formed and they're pushing their way out into the atmosphere, that amount of work is really, really small. If we, express it in joules, it's way out in the decimal places. And so it's not really significant in most cases. It's not significant compared to the amount of heat that is absorbed or produced during the reaction. So that's why, for our purposes, we sort of think of the change in energy and the enthalpy as being one and the same. And when we think of enthalpy, we are typically looking at heat produced or heat lost during a chemical reaction. And that's just because any work done by the production of gases is typically just so very small that it is not really significant compared to the change in the heat energy of our system. All right, so we're looking at here. So again, this is just an example of our delta H follows the same sign convention. So here, these reactions are giving us specific values for our energy change. And so here it's on the product side, so it's exothermic. So here my delta H is going to be a negative 285.8 kilojoules. And then likewise down here, my energy is showing up as a reactant. And so it's endothermic, energy going in. So there my delta H will be a positive 40.7 kilojoules. Now, one of the things we'll see is that we use some subscripts with delta H when we're talking about specific types of reactions. So we want to look at that because you'll have some problems where it'll say, okay, we're going to combust. In this case, this is giving us butane. We're going to combust butane, and it'll just give you the heat of combustion. And so your first thought will be, oh gosh, do I need to write this balanced equation? And it's like, no, the key thing is if it's giving you a heat of combustion, that is the delta H for the combustion reaction with that substance, and it's balanced so that there is a 1 on the substance being combusted. So that if you have a delta H of combustion, that is the energy that is released by burning 1 mole of that substance. Okay, likewise, heats of formation, and we're going to talk a lot more about those later on in the unit, but a heat of formation is the delta H for the reaction where it's a synthesis reaction where you are producing a compound from its elements. And it's always balanced so that there is a coefficient of 1 on the product. So if you have a heat of formation for a substance, that is the energy required to produce 1 mole of that substance from its elements. Likewise, heat of fusion. I think we've mentioned fusion before, but just as a reminder, fusion is melting. So if I have a heat of fusion, that is the energy required to melt 1 mole of that substance. And then likewise, heat of vaporization, that is the energy needed to vaporize 1 mole of that substance. Now, we're going to talk and do some calculations with breaking and forming chemical bonds. And so the key thing you want to think about when you're thinking about a reaction, it is the delta H for a reaction is the net energy change when we look at the energy that is required to break the bonds of the reactants, and then the energy that is released when the product bonds are forming. So breaking bonds requires energy. Bond formation releases energy. Okay, and then your delta H is basically we're looking at the energy required versus the energy released. And so if the energy released is greater, then we have an exothermic reaction, a negative delta H. If the energy needed to break the bonds is higher than the energy released when the products form, then we have an endothermic reaction, or a positive delta H. Okay, so let's look at, these are just kind of a couple of rules in dealing with things that have a delta H with it. So we're starting out with this. So this is our heat of fusion, or our melting equation for water. And so if I reverse it, so if I flip this reaction, instead of melting, now I'm writing a reaction for freezing. If I flip a reaction, the energy required, the amount of it is still the same. It's just that it's going to go a different direction. So if melting is endothermic, right, to freeze it, I'm removing that same amount of energy. So it's exothermic. So if I flip a reaction, I'm going to change the sign. Okay, keep the value the same, but the sign changes. And then also, the delta H value that we have, it goes with that balanced equation, the way that it is balanced. And so if I multiply through, which when we get to Hess's law, you will be doing this sort of thing. If I multiply through an equation, then I also have to multiply through the delta H by the same amount. So in looking at that up here, right, we said that it takes 6.01 kilojoules to melt 1 mole of water. And so down here, if I change the balancing by multiplying through, then it makes sense that if it's 2 moles of water, then it's going to be 12 kilojoules of energy that's required. Okay, so let's look at how we're going to use these delta H's in calculations. And the nice thing is, we're just going to be back to using ratios, like what we did before. So here I have 266 grams of phosphorus, and so P4, so 30.97 times 4. So I get, we're just going to round, about 124 grams per mole for P4. So that means I have 266 divided by 124. So 2.1 moles of P4. And I want to know how much energy is going to be released. Well, from my balanced equation, the other side, the other ratio, I'm going to have same units, kilojoules to moles of P4, and my balanced equation says that 1 mole of P4 releases 3,013 kilojoules. Now, pay attention here, because this will, in your quest problems, a lot of times the sign of your energy will be implied in the problem. So here it says how much heat is evolved. That means they are just wanting the quantity. I don't need to put the negative sign on it when I put the answer in, because the negative sign is implied. So I have this times 2.1. So I get that 6,327 would be my kilojoules that are evolved. So the sign is implied in the question. So I don't need to, if that were a quest problem, I wouldn't need to enter that as a negative. All right, let's take a look at this one. Here it says I have 1,000. I want to know how many grams of aluminum can be formed when I have 1,000 kilojoules of heat formed. Well, my balanced equation, of course, that gives me moles of aluminum to kilojoules of heat. And it says that 1,676 kilojoules of heat are needed to create 2 moles, right? It goes with the balance of the equation of aluminum. So that divided by, so I'm getting 1.19, and that's my moles of aluminum, and then times its molar mass, and I get around 32 grams of aluminum would be produced with that much heat. Okay, so here we have 1 kilomole of hydrogen gas and to energy, and our energy is in calories. So I'm going to go kilomoles of hydrogen, or actually moles, let's do. So kilomole would be 1,000 moles of hydrogen to, oops, not kilojoules. This is in calories. So since it doesn't say it has to be in kilojoules, we'll just leave it in calories. So the other side, I'm going to do moles of H2 to calories. And so here it says 1 mole of hydrogen is 68,320 calories. And again, the negative sign is implied because it says how much heat is given off. So I'm just going to work with the values. And so it would be 68,320,000 calories would be the amount given off. Okay, and that is the end of our first lesson in Unit 8.